Ah, isn't this nice? Roasting marshmallows next to the surface of one of the warmest stars known to mankind, and not having our molecules ripped apart due to the heat. What do you think, Demetrios?
Warning. Core overheating. Nuclear meltdown imminent. Warning. Core overheating. Nuclear meltdown imminent. Warning. Core overheating. Nuclear...
Where the heck are we in? What the heck is that?
Ah, Demetrius, you're back alive! Welcome to the end of society as we know it.
What the heck was that?
That's one of the many pulsar's dank blasts of death shooting by, otherwise known as a regular electromagnetic pulse.
Wait, is that thing rotating?
Yep.
Oh yeah, we learned about this in Mr. Young's radical science class. Pulsars are just neutron stars.
And that's one of the most densest objects in the universe. It might be the size of Toronto, but half the mass of 1.5 of our very own sun.
With my calculations, one sugar cube of pulsar material is equivalent to 100 million tons. Why isn't this thing ripping us to shreds?
The power of video editing, Demetrios. The power of video editing.
What type of pulsar is that anyways?
Oh, this is one of the least significant rotation-powered pulsars. We don't even need to think about this one too much. We'll be using the magic of video editing to visit acceleration-powered pulsars and magnetars.
Wait, where's Earth?
Oh, that's probably destroyed by one of the dank blasts we just saw. You think global warming's bad for the atmosphere? Wait till you see what high energy astroparticles and a bit of centrifugal mechanism of acceleration does to it.
Well, if we're out here, we might as well finish the math assignment.
Fine. The pulse of a pulsar can be modeled by this graph.
This specific star releases radio radiation. From Mr. Young's dank grade 10 science class, you'll remember that radio waves are part of the electromagnetic spectrum.
Since pulsars are so fast and shoots out into every conceivable direction in 3D space, science graphs them in observation periods.
This is known as a radio pulsar, aka the rotational pulsar. It appears to emit a short pulse of radio radiation with a pulse period between 1.4 milliseconds to 8.5 seconds, then disappears as the pulsar is rotating. In reality, this is one continuous beam, but as the pulsar rotates, it escapes human telescopes, so we cannot graph it.
Of course, there is a whole lot of math in this sort of physics, but using this graph as a sample, we can determine the graph of the equation to be this.
The amplitude represents how the power pulse will be. In this case, it will be very powerful because of a small period.
The period represents how long it takes to repeat, so the faster it repeats, the more powerful the pulse is.
The equation on the axis is when the power of the pulse is the same as when it came from the star.
Anyways, isn't this a wonderful sight? No worries. We just have to check out 2 more chilling pulsars. And now we're here at an accretion-powered pulsar.
X-ray pulsars, or accretion-powered pulsars, release X-ray pulses instead of dank death blasts from radio waves. The totally hip X-ray periods range from as little as a fraction of a second to as much as several minutes.
This means we can't model a graph the same way as we modeled the last one. As this period continuously changes, we can only model portions of it.
This was the only graph that our spectacular space computer could extrapolate that follows a sine graph.
The difference is caused by the radio pulsar moving so fast, and the laws of physics tend to break down in areas of high gravity. Wait, why am I explaining this? We don't understand it, you don't understand it. None of us are Dr. Neil deGrasse Tyson. Anyways, let's go check out the final, best, most powerful, probably the most dangerous magnetar. Welcome to a graveyard!
Wait, is that thing dying?
Yep, it's powered by ripping itself apart. Since it's spinning so fast, the magnetic field decays, which powers the emission of high energy X-rays and gamma rays. So, it's killing itself to shoot out things.
Oh yeah, that's pretty small too. At only 20 kilometers in diameter, it has the mass of 2 to 3 times the mass of a sun.
As a matter of fact, it's so rank, not even the power of video editing will save us. We're gonna get our molecules ripped apart in a few seconds, so we might as well explain everything before we die. Now we're in heaven, Demetrios.
More like hell.
So,
Eternal pain and suffering is coming towards me. I can feel my soul being burned.